To kick off the afternoon, we have Alexander
Hulpke.
Hulpke.
Yeah.
Okay. I realized I've never said it out loud.
Yeah.
Was,
There's always a first time.
Right. Yeah, who's going to give us 2 lectures, one today and one on Wednesday?
I thought tomorrow.
Oh, tomorrow?
Yeah.
Maybe tomorrow. The schedule has it right. I don't have it in my brain. On computational.
Great. Yeah. Thank you very much for coming. Thank you very much for the opportunity to talk. Yeah. Why 2 and 3? 2 because we changed the schedule and it became 2. 3 you will see in a little moment why there are three parts. Yes, my work is, I'm grateful to NSF, which is supporting my work, and I actually have a really cool picture with an NSF logo on. So, these slides are on, in part are, in part will be on the web, so you don't need to take notes so far. Only what I think I will get through today is on there, and tomorrow there will be more. So, the first part, that's the first part of the 3. This is in some way the view from 15,000 feet. Group theory. Let me start with a few things you probably know, but just to fix language, I'm interested in groups. A group is a set of elements with an associative multiplication. Such a set is called, if I only have an associate multiplication, it's called a semigroup. What I can always do if I have a semigroup, if there isn't an identity element, I can always add it. That I basically get for free, and then I get something which is called a monoid. But in a group, I also want to have inverses. It turns out in a group, inverses, they are unique. It's left inverse, right inverse, and they are the same. Examples you all will have seen: symmetries of objects, permutations, invertible matrices under multiplication. Groups are not always commutative, and why do I care about groups? Because there are interesting cases, sets of permutations of matrices, sets of symmetries form interesting structures, interesting both on their own in finding out the structure of these objects, but also interesting because they tell us something about objects. If I know the symmetries of an object, I learn something about the object, or I can use symmetries to reduce the size of a problem. And it turns out that somehow this part of the definition, these conditions are sufficiently restrictive to both have enough structure that one can prove interesting things about the structure and actually have enough restrictions on the structure that there isn't just an awful mess. On the other hand, they are weak enough that there are a lot of interesting instances. If we have as always in algebra, if we have some kind of structure, we might want to look at substructures which are invariant under the operations. That's in this case subgroups. If we have a subgroup, there is one thing which one can do, namely to translate the subgroup by multiplying all elements of the subgroup with one fixed element, and then we get something which is called a coset. It's the translation of a subgroup. It's the analog of not having a plane through an origin, but having a plane which is going somewhere shifted from going through the origin. Any element in the coset we call a representative. A subgroup might be normal. This G should have been an exponent, sorry. If any conjugate of an element, if G inverse NG for any n in n is in there, and the important thing about normal subgroups are, first, in this case, we can take cosets of the subgroup and multiply them, and we get again a group structure. And if we take a structure-preserving map, which is called a homomorphism, the kernel of such a map will always be a normal subgroup. Right, groups are interesting because they can act on objects. A group action on a set formally is a map which goes from the Cartesian product of the set and the group, again in the set, to a point and a group element we assign an image, and what we want is that the identity element of the group maps every point to itself, and that a product maps as we would expect, first with the one element, then with the other one. I'm acting on the right because if I would be acting on the left, I would have to put more parentheses here, which gets slightly messy. If we are acting, but that's just a notational thing, that's not something to worry about. If a group acts on a set, we can look at the orbit of a point. The orbit of the point are simply all the images. Dual to the orbit, we have the stabilizer. It's the group elements which map one point. The stabilizer of a point omega is the group elements which map a point to itself. And the duality actually plays out quite nicely in what is called the orbit stabilizer theorem. Namely, there is a bijection between the orbit of a point and the cosets of the point stabilizer. Namely, two elements G and H lie in the same coset of the point stabilizer if and only if they map a point, the stabilized point, to the same image. In particular, we get that the order of the group is the length of the orbit times the order of the stabilizer. Okay, that's probably stuff you've all seen at least once before. Yeah, so what I want to talk about is computational group theory. What is this? It's a study of algorithms for solving group theoretic problems, and there are related problems in related areas, number theory, combinatorics, where groups arise naturally. And there are two viewpoints how one can get to this. One is a theoretical viewpoint. What is possible to compute? What's the cost of doing certain computations? And there are interesting connections to computer science. For example, if you look at graph isomorphism, which is a very prominent problem, if you look at isomorphisms from a graph to itself, they form a group. That's the automorphism group. So there are obvious connections to group theory there. A second strand is a very practical strand. Someone might come with a group. An algebraist, a topologist, if we look at fundamental groups of spaces, comes with some description of a group and might want to get some information about this group. And indeed, this has been the source of, or one of the points where computational group theory grew from. There has been something in group theory, the classification of finite simple groups, where people in the 60s, 70s found quite large groups which had very nice properties, and they wanted to find out more about these. But these groups were so large that it's hopeless to do calculations by hand. So there was a very practical need to have computer tools to do calculations with these groups. In general, I will mostly talk about finite groups. There are algorithms for infinite groups, but in these cases, basically one always needs to restrict to some finite cases because that's what computers can do. There are some software engineering aspects towards building algorithms. I basically won't do this here. I will just talk about the mathematics and some aspects of computer science. This is not just, well, to have it practical, you need to have implementations. There is software which implements a lot or most of these algorithms which I'm going to describe and many more. There is a system Magma which comes from a predecessor Cayley. There is a system GAP which I'm involved in. This is also what is used in Sage. In this talk I'm not going to talk about GAP, but if you're interested in how to do things there, please talk to me. I'm very happy to show you more examples than you probably want to know. Right, so let's look at what does computational group theory do from 15,000 feet. The basic stack of routines we have on the very bottom element arithmetic and testing equality. That's almost not computational group theory, right? Multiplying matrices, you know how to do it, you know how to check whether two matrices are equal. But then it becomes more interesting, what's the order of a group? How do we test membership in a subgroup? How do we evaluate a homomorphism? Which is, if the homomorphism is given on generators, that basically means express an element as a product of generators. And somehow there is a slight separating line here. This is where basic algorithms are, which really use the structure of the elements, the kind of elements where one works with. And then higher level algorithms in some way try to use these routines as basic building blocks and then are independent of the representation. You might want to find out particular things about the group, conjugacy classes, subgroups, character table, find out particular properties. You might want to build libraries of groups. You might want to test isomorphism of groups. Well, you might even have here some own calculation. You might want to see, is there a counterexample to my conjecture? Okay, so that's the basic thing. That's in some way the levels of tasks which one might want to do. I will mostly focus on what is happening here because, yeah, things become more complicated. Right. I said this depends on how the group is represented. So let's briefly look at how can one actually represent group elements. And these are probably not all ways, but some of the ways which are used. We might have symmetries of some discrete object. That's the natural way how groups arise, the symmetries of a cube or so. We might have, and that's how they arise in topology, as finitely presented groups, words, and generators. And we might have something where we don't even care about how they are represented, but just about that we have a multiplication and an equality, multiplication, inversion, and an equality test. And that is what is called a black box group. You might ask, why forget about other things? Why forget that it is a set of matrices or set of permutations? But it turns out that some theoretical analysis actually becomes easier if one forgets about some details there. So black box groups, it's an abstraction from the representation, concrete representation of elements. They are technically, we assume we have a bound for the order of the group, we have arithmetic equality test. In this case, one can test bounded order in polynomial time, but not order. Because, I mean, bounded order if we have the bound as part of the input. Well, I mentioned already permutations, we have matrices. With words, the first example, or one of the first examples of a group you might have seen, might have looked like this, the symmetries of a square, where we have a rotation, which is called R of order 4. We have a reflection, which, because rotation already uses the R, and because reflection in German is called Spiegelung, is denoted by S. So we have S has order 2, and then they say, typically, oh, there is a relation that if we do RS, that's the same as SR inverse, and from that we can form a normal form. And that is a quite important subclass of words in generators. These are groups where we can bring words into a normal form. In these lectures I won't talk much about these groups, or they will come up on the site, but actually polycyclic generating sets, which I will get to next time, are a special case of this. Basically, this is very hard. This is basically a case where it is potentially not solvable in a Turing machine model. This is something which allows for very efficient algorithms. Yes, and the three lower level of this stack, which I have described, they will depend very much on how the elements of the group are represented. In some cases, one might want to actually change representations. In GAP, we call this a nice monomorphism that we have through an action or evaluating words map from one class of group to another. class of groups and actually say, instead of calculating in the original representation, calculate in the other one. And yeah, in part, so therefore these routines in part build on each other. In some cases, software currently will always translate. In some cases, it might translate to different representations. And if you're interested in concrete problem solving, basically the lower you can get here, the more efficient your calculation will be. Yes?
What's nice about the monomorphism? What property is it?
So the question is, what is nice about the monomorphism? In some way, it's the monomorphism is into a nicer representation, into a representation where the calculation becomes more effective. So if you have a finitely presented groups where your elements are words, then even just testing equality can be a very hard problem. If someone promises you, here is a monomorphism into a group of permutations, your letter A corresponds to this permutation, your letter B corresponds to this permutation, equality testing suddenly becomes very easy because you just evaluate the product in the permutations.
So the codomain is the nice.
Yes, yeah. So it would be too nice domain monomorphism. Yeah.
What's the dotted orange arrow?
Oh, the dotted orange arrow is, yeah, maybe it also should be drawn through that. In some cases here, that was basically, this slide is reused from a talk which was more specific about GAP. So here, this is something GAP will do automatically. This is something you can ask GAP to do, but it is not doing this by default. So that's why it was dotted. Okay, and that basically is the 15,000 feet view. So let's move a little bit closer. 10,000 feet, let's look at actually what is used for implementing these bottom three layers. And the crucial tools there are generators and subgroup chains. So if we go briefly back, what is a group? Well, a group, the definition in the textbook says it's a set of elements with associative multiplication, identity, and so forth. So how do we calculate in a group? If this was a cube and we wanted to look at symmetries of a cube, well, how do we multiply? The first examples in the textbook give names to rotations. If we rotate clockwise through the top front right corner, and then we rotate the front face, we get the rotation has some other name. That works, but is rather tedious because every element has a name. How do we give names to all elements? If we have a group with 10 to the 7 elements, yes, we can give them numbers, but that doesn't help us much. We also would need to store the full multiplication table, and that's what the textbook initially does. But if your group has about easily 10 to the 7 elements or so, that is just not feasible. Just as a back of envelope calculation, if we have permutations, to store a permutation on n points, we need roughly n times log n bits. If we have permutations on 10 to the 5 points, we have 8 gigabyte of memory. We can store about 40,000 elements, 40,000 permutations. But if we have, on the other hand, 10 to the 5 elements, the multiplication table would take 10 to the 10 bytes, at least. So that gets very quickly to magnitudes which, even for $6,000 from Apple, you will not have a machine which can store. And yeah, so this model with a multiplication table is not really feasible if you want to do practical calculations. So therefore we're doing something something different. We don't store, and it's not a new idea. In linear algebra, you don't write down all elements of a vector space. You write down a basis. So we want to store only generators of the group And that suddenly gives us an enormous reduction. Roughly only the number of generators we need in the worst case is a logarithm in the group order. So if we have a group of order 10 to the 5, we have only logarithm of 10 to the 5 many generators. And some further data which allows us to reduce calculations to the generators. Calculations like order of the group, testing membership, evaluating homomorphisms. And that's exactly what is done in other cases. That's done in vector spaces, you look at a basis. If you look at ideals in polynomial rings, you look at ideal generators. You don't try to write out all polynomials up to a certain degree or so in the ideal. Well, two caveats with this. The first, if that is the model we are using, the multiplication table is exponential size in the number of generators. I get about once a year a paper to referee or to review where someone designs a new algorithm which is for groups based on having the multiplication table. Yes, that's nice, but if you're using that model, you first buy yourself an exponential speed up compared to the other model, and in practice you're really restricted how large groups you can represent on the computer. So I would like to argue that the generator model actually, at least if you're interested in any practical calculation, the generator model is a more relevant model. Well, with that, of course, there is another very, well, slight or not that slight problem there. If we express things in generators and we just look at the easiest case, the case of a cyclic group, basically we have a discrete logarithm problem. And I'm not planning to solve discrete logarithm in polynomial time. So, if we are interested in polynomial time, this is something one might have to skirt around. It is done in some cases that people just say they assume a discrete logarithm oracle, which is saying I don't want to deal with this problem, I delegate to someone, to something which can do it. But more realistically says up to basically we have only a limited number of discrete logarithms and the rest limited by a polynomial or constant bound, and the rest is polynomial time. Okay, so the model I'm going to talk about is group represented by generators. I mentioned already group actions are a basic tool for working with groups, so we should look at what happens if we are acting with generators. So, a set of generators, it's a set of elements so that every element of the group can be written as a finite product of these elements and their inverses. I'll be a little bit sloppy with the inverses. If you're worried about this, assume the set of generators is closed under taking inverses. Actually, if the group is finite, we don't really need to worry about the inverses because every element has finite order, and if we just multiply it with itself, at some point we end up with the inverses. Yeah, or assume the set generating set includes the inverses. So, what about getting an orbit? What about getting a stabilizer of a point? Well, if a group acts on a set, every element of the orbit, every image of the point omega is the image under some group element, which is a product of generators, and by the conditions we have for a group action, where acting with a product means act with the factors one by one, it means every image is obtained iteratively as an image under generators. And that's something you have probably seen in puzzles. That's exactly what Rubik's Cube puzzle asks. You have a group element, a permutation of the faces, which is a mess, and you have particular generators, namely the ones which you can actually physically do with your hands without disassembling the cube. And it asks, how can you express the element as a product of generators? It's an interesting problem. alas, the optimal solution for this, the only one I'm aware of, if you really want the optimal solution, you need to do exhaustive search, trying out all possibilities. A non-trivial problem is how could one design good strategies for finding short words. There hasn't been much work done on this.
Is that like wadded up chewing gum? What is
A nut. It's a hard nut. Sorry, yeah, this is design trumping. So for the recording, this was the question whether this was chewing gum. No. This is your brain on. Okay. So, but going back here, if we look at the orbit of an element, every point in the orbit is obtained by iteratively mapping with generators again and again. And that gives us something which is called the orbit algorithm. We have a Q, we initialize with the point whose orbit we want, and we go through the Q, any element delta in the Q which we haven't yet processed. We calculate images under all generators, well, and inverses. And if it's new, we add it to the Q. If the orbit is finite, this has to finish at some point. So that gives us, when it finishes, obviously we have the whole orbit, because every image of every element in the Q under every generator, that means the image of omega under any product of generators will be contained in there. We can also, if we don't just calculate the images, if we keep track how we obtain images, then we get a transversal of transporter elements, which actually for any element in the orbit gives us an element which would map omega to that particular element, and we can even keep track how this is written as a product in generators. If we take the regular action, a group acting on itself by right multiplication, this would give us a constructive membership test, however at high memory cost, because we would have to store the whole group, and that's not really what we want to do. Okay, but that's the orbit algorithm. The next thing I want to do is, I said we have orbit, we have dually the stabilizer. In this model, we should be able to get generators for the stabilizer. How can we do this? Well, one of the basic ideas in mathematics, which comes up in multiple areas, is that you can go, if you go around and you come back to the place where you started with, something interesting happens. That's what complex analysis does. You integrate along a closed curve. That's what topology, algebraic topology does. If you look at the fundamental group, you look at paths from a path to itself. We can use the same idea here. Let's suppose we're calculating the orbit. We have found some element delta in the orbit, and we had found this transporter element t by keeping track that we know t will map omega to delta. We now map delta under a generator G, and we get an element gamma, and we observe, oh, gamma is not new. Gamma is something which we had already, well, because we had gotten it under some other transporter element S. Well, because the group has inverses, that's really where the inverses comes in. This is where group theory starts diverging from semi-group theory. We can go this way, we can go back through S inverse, and we are back at omega. That means Tg S inverse maps omega to omega. That is an element of the stabilizer. So we can find elements of the stabilizer, and there is a nice theorem due to Otto Schreier, which says if you do this systematically for all elements in the orbit and all generators, actually these elements, which are called Schreier generators, give us a generating set for the stabilizer of omega. And by keeping track how the transporters were words, we actually get generators for the stabilizer, even as words in the generators of the group. So the model of having a group given by generators translates. If we start with generators for the group, if we look at, say, the question of a stabilizer, we can again get generators for the stabilizer. A few remarks about the cost. The storage cost, just for calculating the orbit, is the length of the orbit. It's nice to have short orbits. We don't have a guarantee that an orbit is short. We need to identify elements in the orbit to find transporter elements. So we need, this is basically data structure question. We need something like a dictionary to identify which orbit element is not just is an element in the orbit so far, but which element is it, what's the associated transporter. If you calculate with this, well, we do it for all. This is a Cartesian product, number of elements in the orbit times number of generators. Well, you get number of generators minus 1 because you might get also new orbit elements, but the number of Schreier generators is in the magnitude number of generators times length of the orbit, and that is a huge number. That explodes very quickly, that gets very quickly out of hand. So what one needs to do is, one needs to reduce this. You can't do it in general by theory, because if you do this in a generic case of a free group, you really need all Schreier generators. So you will not have a theorem which just uses group theory, which says you can remove some, because there are groups where you really need all. But in finite groups, very rarely are situations where you need all. What is done is we pick only a few elements or a few products of elements, we pick them randomly, and then one needs some verification step for showing that things work. Let me just, before going into this in a little bit more detail, mention one other aspect how one can look at the stabilizer generators. We don't need an orbit calculation. We just need to test whether elements are in the same coset or whether elements are in a subgroup. If we have a subgroup described by a property, this algorithm will allow us to get stabilizer generators. So let's look a little bit more at this question, and basically just to fix some language and some idea. So if we look at algorithms which use randomization, well, there is one. This comes very early when people started to design algorithms. There is the idea of a Monte Carlo algorithm. A Monte Carlo algorithm, well, rolls a die or plays roulette, depending what class of gambling you're interested in. And you might get wrong results, and you might be able to have to play with the probability of an error, but the result might be wrong, just very unlikely to be wrong. Well, that's not really good enough if we want. What we want is we want proven correct results. And basically the tool there is to not just have a random calculation, but to have a verification afterwards whether the result is correct. And with that, one gets a class of algorithms which has been named by Las Vegas algorithms. That's basically Monte Carlo plus verification. In this case, the runtime is an expected runtime, because theoretically it could fail again and again and again. It could fail an unbounded number of times. So we have an expected runtime, but we have a guaranteed proven result. And that's what we want to use and what we are using. So there is a randomized stabilizer calculation, and there is a subsequent verification. I'm not yet telling you how the verification works, but there is a tool which allows us to just use some Schreier generators, do verification, and thereby we end up with Las Vegas algorithms. Right, so what have we done so far? We have looked at the model of a group given by generators, and we have found that we can calculate an orbit, we can calculate generators for the stabilizer, and we can get somehow around the problem of the large number of Schreier generators. So that gives us the idea for a divide and conquer algorithm. If the stabilizers are groups themselves, so if we are interested, for example, in how large is the group, is a group given by generators, calculate a stabilizer, calculate the order of the stabilizer recursively. The order of the group is the order of the stabilizer times the index of the stabilizer, which is the length of the orbit. So that's the basic divide and conquer paradigm which is used in group theoretic algorithms. And if we go for two permutation groups, that's the class of groups for which probably algorithmic theory has earliest been developed to a very satisfactory point of view. The underlying data structure is something which is called a stabilizer chain. So we have a permutation group, a subgroup of the symmetric group on some set omega. I will pick a set of points. I have a set of points. This set of points will depend on the group. You can't say, this is the points I want. So this depends on the group. Such a set of points is called a base if the only group element which maps every point to itself is the identity. Actually, if your group is the symmetric group, base basically means you have all points but one. Why but one? Because if the last one needs to take what is left. But the interesting thing is, if your group is not symmetric or alternating, a base will be much smaller than the size of omega. In general, a base typically will actually be quite short, will be, unless your group is symmetric or very close to symmetric, it's hard to come up with examples where your base is longer than 10 or so. So associated to the base, we have a chain of subgroups, and these are called the stabilizer chain. So we start with the group itself, we take the stabilizer of the first point, in there the stabilizer of the second point, in there the stabilizer of the third point, and so forth. So the last group, because of this condition, the last group will stabilize all the points, and that's the identity. And this chain of subgroups is called the stabilizer chain. How can we compute it? The algorithm for this is called the Schreier-Sims. Oh, sorry, let me mention just one further condition here. This basically means if the identity is the only element which fixes all base points, that base images, if I know the images of a group, of the whole base under a particular group element, this defines the group element uniquely. Because if I had two different elements which did this take the quotient will map every beta to itself, so must be stabilizing. So, for constructing such a stabilizer chain, the algorithm is called the Schreier-Sims algorithm, named after Charles Sims, who first developed this. What it does is, well, start with a point, calculate the orbit, calculate stabilizers, generators for the stabilizer go on. But there is one trick in there, and that is, even without verification, how do we reduce the number of Schreier generators? We don't go through the tree layer by layer, we do a depth-first search. So, we have already some partial subgroups given. Whenever we get a Schreier generator, we compute the orbit, we get a Schreier generator, we go one layer down. We look what is there. If there is nothing, we start with this one element and build an orbit of the next point. But if we have already something, we use that data structure we have so far to do an element test, to check whether that element already can be written as a product of what we have. If so, we throw it away, and thereby one can implicitly reduce the number of Schreier generators and get to a smaller number. So that's a stabilizer chain, and that's very vaguely how one computes it. What can we do with it? Well, if we have such a chain of subgroups and we have transversals that is representatives for the orbits in every point, well, what we can do is we can calculate the order of the group. That was what I had on this divide and conquer cartoon slide, right? The order of the group is simply the product of the length of the transversals, the product of the length of the orbits. So, I can get the order of the group. Next, I can test membership in the group. How do I do this? If I have some element x where I want to check is it in the group, I look at the orbit on the top layer and I look what does this element do with my first base point. If it maps the base point somewhere which actually isn't in the orbit I have, well then I know the element can't lie in there. Because the orbit is the orbit, it's the set of all images. So let's assume it is in the orbit. Well, if it is in the orbit, I have the transversal element which I have as an element in the group which mapped omega to the same image as x does. So I divide off the transversal element, so I get x divided by some element in the group, and this quotient must map omega to itself. So I've now reduced the question, is x in the group, to the question, is this quotient of x with a group element in the stabilizer of omega? And that's a smaller group. And then I'm going through the stabilizer chain iteratively, and the last group in the stabilizer chain is the trivial subgroup. So I'm doing this a couple of times, always dividing off a transversal element, and what needs to remain at the end is an element of the trivial subgroup, the trivial permutation. If it is, the element is in the group. If not, then not. And if I don't just store the transversal element, but I keep track how the transversal elements were written as products of the group generators, I actually have written my element x, if it's in the group, as a product of group generators. So I can factor in group generators. Caveat, this gives us quite long words. If you do this naively for Rubik's Cube, you get words of length a couple of million. So even if you just wanted for heuristics to get some decent words, you need to play some tricks, and basically you need to precede your transversals with short words to try to get short word expressions in there. Okay.
Is it really a word issue or an SLP won't solve this either?
Okay, so the question is this a word issue or does a data structure which is called a straight line program solve it? So a straight line program is basically just saying you allow yourself to calculate intermediate results and use them again. And that would resolve it. Yes. Because you would say the problem is the words grow so long because you get Schreier generators and Schreier generators from Schreier generators, and that builds things up. So if you allow yourself to store intermediate results, everything is hunky-dory. It's just if you're trying to solve a Rubik's Cube type puzzle, no one will be happy if you say, and now you just call subroutine 5 and subroutine 17, and these will take you 2 hours to fulfill. So it's not a problem in practice because you can store these things. It's just if you're interested in this puzzle type problem, that is in principle a question. Okay, what else do we get? I mentioned on the previous slide that we have a bijection between possible tuples of base images and elements of the group. So we can use this enumeration, and the possible images correspond to the orbits, the Cartesian product of the orbits. So a Cartesian product we can enumerate easily. We know how to run through a Cartesian product. Well, actually in multiple ways, but choose your favorite way. That gives you a way to enumerate the elements in the group. To give every element in the group a number to run through all group elements, touching every element exactly once. And with this we can describe all elements of the group through a tree structure, just a tree which basically corresponds to traversing a Cartesian product of possible base images. And we can search through this tree. We can search through the group to find elements with particular properties. And such a search is called a backtrack search. It is exponential time. But it turns out with some further improvements which use the fact that certain sets of elements form a subgroup, actually in practice for permutation groups this works surprisingly well, and we can do things like testing whether elements are conjugate, calculating the centralizer of an element, calculating the normalizer of a subgroup. So in practice, this is a core tool for working with permutation groups. But it's a non-polynomial time tool. It inherently is exponential time. If you come from the theoretical side, this is a big no-no, and you probably say these are useless algorithms. If you come from a practical side, at least for the time being, they're pretty useful algorithms. Yeah, and I mentioned already we use the membership, when building a stabilizer chain, we can use the membership test which we get from, which I described here, to reduce the number of Schreier generators. So that all behaves reasonably nicely. If you have a permutation group of degree at most a few 100,000, well, why do I put the boundary with 100,000s? There isn't anything magic about it. It's just once you get in the millions, at some point, you get still into issues where just storing permutations takes time, takes a lot of space, and you are somehow limited. But maybe even a few million, one can reasonably quickly calculate the order of the group. Calculating the order, building the stabilizer chain actually is always polynomial time. I didn't describe in detail why it is polynomial time, but it's polynomial time with a relatively large exponent. One can do it in Las Vegas polynomial time, which is proven in almost all cases, and I'll talk next time about what the what case is where something isn't done, and that has to do with the verification. So there is Las Vegas, not just polynomial time, but nearly linear time for calculating the order, for building the stabilizer chain data structure. And if you want practical calculations, backtrack search actually lets you work with these groups reasonably well. So there the behavior is quite nice. Well, this doesn't solve all problems, but is a nice toolkit for working with permutation groups. So, permutation groups, however, is not everything. There are other groups. So let's, for example, look at matrix groups. Well, a permutation group acts on points, a matrix group acts on vectors. There is nothing special about calling numbers points. We could call vectors points. We could do the same thing as we did for permutation groups with a stabilizer chain for a matrix group, where we just say the underlying set is not the numbers, the underlying set is a set of vectors in the vector space. Pick a vector, calculate the orbit, or we could do this for groups of automorphisms of a group, where we act on the group. But there is a problem, and the problem is orbit length. I mentioned before on the side slightly sneakily that for orbit calculations to work fast, we want that the orbit is short. If we look at the orbits on vectors of a matrix group, let's say you take SLNQ, n by n matrices over the field with q elements, it turns out all vectors are, but the zero vector are in one orbit. So there our orbit is comparatively long. If you compare this with the order of, this is much closer to the order of the group. The stabilizer is very, very small. If you have permutation groups or in the symmetric group, the stabilizer of a point is comparatively close. It's just at most a factor number of size of the domain. But for vector spaces, the size of the domain isn't really, or the size we want to use is not the number of vectors. It's something like dimension, maybe times number of the cost of storing field elements. So, in this case, if we just take the action of a matrix group on vectors, the orbit length, it gets much larger than the size of the input. If we have matrix generators, we would have roughly, every matrix is n square log n, log q, many entries. So calculating an orbit and calculating a transversal is very costly, both in practice and also and certainly in theory, because here we have something, the orbit length is already exponential in the size of the input. That's not what we would like to do. One could ask, can we do other orbits? Well, we could say, let's not act on vectors, let's act projectively. Let's act on one-dimensional subspaces. And then that action is primitive, we can't reduce further, but that gives us a factor q minus 1 out of here. This doesn't resolve the exponential problem. Are there other actions which would give us short orbits? No, they are not. Theory about the special linear group and about many other matrix groups says, no, there are no short orbits. All possible orbits are long. Why? Because all subgroups have comparatively large index. So, that approach with a stabilizer chain will not work for such groups. So, for matrix groups, something else is needed. Okay, and yeah?
Does it mean that if I wanted to represent the matrix group as a permutation group, that the n would be huge for those groups?
The degree potentially would be huge, yes. If you take the, let's say, 5 by 5 matrices over the field with 7 elements, right? Then you have 7 to the 5 minus 1. What is this? 7 square is 50. 50 times 50 is 2,500. 5 times, so we would get 15,000. Okay, 15,000, but then don't make it 5 by 5. Make it 10 by 10. This grows very quickly exponentially. Yeah, even that, yeah, exponentially or more, yes. So, if I want, I can do that. And in small examples, it works perfectly fine. That's currently still what GAP, for example, does by default. It just tries to write down a group of permutations. And if your groups are small enough, that works perfectly fine. But if you come with 50 by 50 matrices over the field with 11 elements, unless some oracle told you, and that group is really small, basically your calculation will run out of memory when enumerating the vectors for the orbit. That's the problem of using stabilizer chains for matrix groups. And therefore, for matrix groups, one needs some other tool. And it turns out that other tool, which is called a composition tree, actually is a different way of using divide and conquer. It gives us more structural information. It actually helps us to go away from the purely combinatorial model of having points which are mapped by permutations to each other. It goes much closer to structural information using the structure of the group, and ultimately reduces to a situation where we are using where we, in the best of all cases, are only using linear algebra and known information. But yeah, that's not part of this chapter, and I think looking at the time, that might be a good point where to stop. And I'll continue tomorrow.
Any more questions for Alex?
So in principle, when you're doing a stabilizer computation, you describe it as a permutation group and
Yeah.
describe it as machine. But as long as you could check membership in that group, you could do this. In particular, you wouldn't have to change to a permutation domain for your matrix group. You could just do it on the matrices.
Yes.
But in practice, is there a reason that you should turn the vector space first into a permutation domain? Does that somehow simplify the actual computation, or should you just treat it on the actual explicit matrices?
Okay, so the question is, when doing a stabilizer calculation in a group of matrices, should you do it with matrices or should you translate to permutations? And that depends a little bit on how large your problem is and where your obstacles lie. So, what do I mean where your obstacles lie? If your stabilizer ends up very small, you can just calculate the orbit, you will get Schreier, using the orbit algorithm, you get Schreier generators, you take the matrices you get as Schreier generators and you process them ad hoc. If you want to use a data structure for the stabilizer to discard redundant Schreier generators, then you probably want some data structure that you can work with that stabilizer. And with the models we've seen so far, that is the model of permutations, then you might want to write it down as permutations. The other opposite obstacle is, and that's again because the degree grows, 50 by 50 matrix over the field with 11 elements isn't very large to write down. Or if we even take the smaller one, what did we say, 5 by 5 matrices over the field with 7 elements is about 15,000 points, right? Storing a 5 by 5 matrix over the field with 7 elements, well, in 1 byte we can store 2 elements. We can actually store them even more compact. But let's say we store 2 elements, two field elements in a byte. Then for 5 by 5, 25, we need 12 bytes for a matrix. Okay, give it a little bit more, let it be 20 bytes because there is some extra data. It's 20 bytes for a matrix. If we store a permutation on 15,000 points, we need more than 1 byte per point, we need at least 2 bytes. So we need 15,000 times 2 bytes, this is 30K. So the cost, if you want to decompose into generators, if you want to store transversal elements, and so suddenly your storage cost grows very much. So if that is a problem, you might want really to stay with matrix, also want to stay with matrices. So the idea, and that's where I want to go next time, is really how can we stay with matrices as much as possible and use permutation groups only in cases where they are more harmless. And it turns out the case where they are more harmless is if the groups are simple. But yeah, that's for tomorrow. Yeah?
I saw that towards the beginning of your slides, you colored theory in red and practice in green. Can you comment about your choices of these colors?
Oh, they're nice colors, right? No, there is, this is... Yes, I will repeat the question. So why did I color theory in red and color in green? And this goes back to a conference in the mid-1990s where, initially computational group theory really evolved in 2 different strands, one coming from theory, one coming from practice. And because the main protagonists of both strands were on different sides of the Atlantic, they didn't initially talk to each other much about this. And And since the early 1990s, these strands have been brought together. But in one talk by Latsibabai, they were described as the red strand of theory and the green strand of practical calculations. And yes, that's where these colors come from. And you can see the person who's wearing a green shirt comes more from the theoretical side, and the person wearing a reddish shirt comes from the practical side.